Hey everyone, Partha here. I love building things. I love taking an idea, a pile of raw materials, and turning it into something functional, something real. But here's a secret I've learned over years of making. Building is only half the story. The other, equally important half, is keeping it running. That's where the unsung hero of the engineering world comes in: maintenance. It's not just about fixing things when they break. It's a deep, fascinating discipline dedicated to reliability, longevity, and performance. Think of any complex machine you rely on: a car, a power plant, even the servers that bring you this video. Its ability to perform day in and day out is a testament to brilliant maintenance engineering. Without it, everything eventually grinds to a halt. Now, you might think maintenance is a one-size-fits-all deal, but that couldn't be further from the truth. The world of maintenance engineering is a rich tapestry of different strategies, each with its own philosophy, tools, and applications. It's a toolbox, and a master craftsperson knows exactly which tool to use for which job. You wouldn't use a sledgehammer to fix a Swiss watch, right? The same principle applies here. Understanding these different approaches is what separates a good engineer from a great one. It's about making smart, informed decisions that keep the gears of progress turning smoothly and efficiently. So today, we're going on a deep dive. We're going to open up that toolbox and examine 9 key maintenance strategies that every engineer, maker, and curious mind should have in their arsenal. We'll explore everything from planning for the inevitable to predicting the future with incredible technology. We'll look at the philosophies that drive these methods, from reactive fixes to proactive perfection. By the end of this, you'll have a comprehensive map of the maintenance landscape, ready to tackle any challenge and keep your own projects running like a dream. Let's get started. First up is the strategy most of us are familiar with, even if we don't use the fancy name: preventive maintenance, or PM. This is the bedrock, the foundation of a reliable system. The core idea is simple and elegant. Do the work before it becomes a problem. It's based on time, cycles, or mileage. Think of changing the oil in your car every 5,000 miles, whether it seems to need it or not. You're not waiting for a warning light. You're following a schedule designed to prevent that warning light from ever coming on. It's about replacing a part that's known to wear out before it has the chance to fail spectacularly and take other components with it. In practice, this means creating a detailed calendar of tasks: inspections, lubrications, cleaning, adjustments, and component replacements. It's a disciplined approach that requires meticulous record-keeping and a deep understanding of your equipment's life cycle. The beauty of PM is its predictability. It reduces the chaos of unexpected breakdowns, extends the life of your assets, and often improves safety. The trade-off, of course, is that you might be replacing parts that still have some life left in them, or performing service that isn't strictly necessary at that exact moment. But for many, that cost is a small price to pay for peace of mind and operational stability. Now, let's get into the really cool, almost sci-fi stuff: predictive maintenance, or PDM. If preventive maintenance is about following a schedule, predictive maintenance is about listening to what the machine is telling you right now. It uses advanced monitoring and analysis tools to track the actual condition of the equipment in real time. We're talking about using things like vibration analysis to detect the faintest imbalance in a spinning motor, or infrared thermography to spot a circuit that's overheating long before it fails. It's like being a machine doctor, using a stethoscope and an X-ray to diagnose a problem before any symptoms appear. This strategy is a game changer because it allows you to act at the perfect moment, not too early, not too late. You're not just guessing that a bearing might fail in the next month. You're analyzing data that shows its performance is degrading and it's likely to fail in the next 48 hours. This data-driven approach is incredibly powerful. It maximizes the life of your components, minimizes downtime to only what is absolutely necessary, and can prevent catastrophic failures by catching them at the embryonic stage. The investment in sensors, software, and skilled analysts can be significant, but the return on that investment, in terms of avoided costs and increased uptime, can be astronomical. Alright, so we've talked about planning ahead and predicting the future. But what happens when, despite our best efforts, something just breaks? That's where corrective maintenance comes in. This is the classic "if it ain't broke, don't fix it" approach, taken to its conclusion. It is purely reactive. A component fails, the machine stops working, and a team is dispatched to diagnose the problem and perform the necessary repairs to bring it back online. There's no schedule, no prediction, just a problem and a solution. Every mechanic, technician, and tinkerer has lived in this world. Now, it's easy to paint corrective maintenance as the villain of our story. It's often unplanned, leading to chaotic scrambles and significant downtime, which can be incredibly costly in a production environment. A failure of one small part can cascade, causing extensive secondary damage that is far more expensive to fix than the original problem. However, it's not always the wrong choice. We have to be honest here. For some equipment, it's the most economically sensible path. But we'll get to that later. For now, understand that while most modern strategies aim to avoid corrective maintenance, it will always be a necessary part of the toolkit for handling those unpredictable, unpreventable failures. So far, we've looked at strategies that apply a single philosophy. But what if you have a massive complex system, a whole factory, or an aircraft, for instance? You can't just apply one rule everywhere. This is where reliability-centered maintenance, or RCM, comes into play. RCM is a high-level, corporate-level strategy. It doesn't ask, how should we maintain this part? It asks, what does this part do, how can it fail, and what are the consequences if it does? It's about systematically figuring out the best maintenance strategy for each individual component based on its criticality to the overall operation. The RCM process is intensely rigorous. You identify the functions of a system, the ways it can fail, these are known as failure modes, and the effects of those failures. Then you classify the consequences. Are they a safety hazard? Do they stop production? Or are they just a minor annoyance? Only after this deep analysis do you select the most appropriate and cost-effective maintenance task. A critical component might get the full predictive maintenance treatment, while a less important one might be left to a simple preventive schedule or even run until it fails. RCM is the grand chess game of maintenance, optimizing resources to achieve the highest reliability where it matters most. Now, you might be thinking, condition-based maintenance sounds a lot like that predictive stuff you talked about. And you're right, they are very closely related. Think of them as siblings. Both rely on monitoring the actual state of the equipment. But there's a subtle and important distinction. Predictive maintenance, or PDM, is about using data trends to forecast a failure point in the future. Like, this bearing will likely fail in 200 hours. Condition-based maintenance, or CBM, is more direct. It's based on hitting a specific predefined limit. When the vibration exceeds X or the temperature rises above Y, then we perform maintenance. Think of it this way. CBM is like the fuel gauge in your car. It doesn't predict you'll run out of gas next Tuesday. It simply tells you, your fuel level is now below this preset limit. It's time to take action. This approach triggers maintenance only when it's genuinely needed, as indicated by a real-time condition. This avoids the potential waste of scheduled preventive maintenance and is often simpler to implement than the full-blown forecasting of predictive maintenance. It's a highly efficient strategy that ensures you're not over-maintaining your equipment, saving both time and money while still being responsive to the machine's actual health. So far, we've mostly talked about maintenance as a job for a dedicated team of specialists. But what if we changed that? What if we made reliability everyone's responsibility? That's the revolutionary idea behind Total Productive Maintenance, or TPM. This is less of a technique and more of a cultural philosophy. It aims to integrate maintenance into the very fabric of the manufacturing process by empowering machine operators to take ownership of their equipment. This isn't about turning every operator into an expert mechanic, but about involving them in the day-to-day care of their own workspace. Under TPM, operators are trained to perform routine tasks like cleaning, lubrication, and basic inspections. They become the first line of defense, able to spot small issues like a strange noise, a minor leak, or unusual vibration long before they become major problems. This creates a powerful sense of ownership and partnership between the production floor and the maintenance department. The specialists are then freed up to focus on more complex repairs and proactive improvements. The goal of TPM is the pursuit of perfection: zero breakdowns, zero defects, and zero accidents. It's a holistic approach that boosts productivity by making everyone a stakeholder in the machine's health. Let's talk about risk. In any complex system, not all failures are created equal. The failure of a light bulb in a storage closet is, well, just an inconvenience. But the failure of a primary safety valve on a pressure vessel, that's a catastrophe. Risk-based maintenance, or RBM, is a strategy that formally acknowledges this reality. It uses a systematic process of risk assessment to prioritize all maintenance activities. It asks two fundamental questions for every potential failure. What is the likelihood of this failure happening? And what are the consequences if it does? The combination of likelihood and consequence gives you a clear measure of risk. Maintenance resources, time, money, and personnel are then allocated to mitigate the highest risks first. A high likelihood, high consequence failure mode will receive the most intensive and sophisticated maintenance attention, maybe even a combination of predictive and preventive tasks. Conversely, a low likelihood, low consequence failure might be deemed an acceptable risk and receive minimal attention. RBM is a powerful tool for optimizing your maintenance budget, ensuring that your most critical efforts are focused on protecting safety, the environment, and core business operations from the most significant threats. All the strategies we've discussed so far, even the predictive ones, are still in a way about dealing with symptoms. A bearing is wearing out, so we replace it. A motor is vibrating, so we balance it. Proactive maintenance takes a giant leap further up the chain. It's not about fixing symptoms. It's about relentlessly hunting down and eliminating the root causes of failure in the first place. It asks the powerful question, why did the bearing wear out prematurely? Was it misalignment, improper lubrication, a flawed installation procedure, contamination? This is really a detective's approach to engineering. It involves deep analysis, precision measurements, and, honestly, a refusal to accept it just wore out as an answer. The goal is to correct the underlying conditions that cause wear and tear, thereby extending the life of the machinery far beyond its standard design life. This might involve things like precision alignment of shafts, balancing components to near-perfect tolerances, or installing better filtration systems. Proactive maintenance is the ultimate form of prevention. It's about creating such a perfect operating environment for your equipment that failures become a genuine rarity, not a statistical expectation. After all this talk of high-tech prediction and proactive perfection, I want to talk about the simplest strategy of all: run to failure. And yes, this is a conscious, deliberate strategy, not just neglect. Sometimes, the most cost-effective and logical thing you can do is to let a piece of equipment run until it breaks, and only then do you repair or replace it. This sounds counterintuitive, right? But think about it. Does it make sense to spend time and money performing preventive maintenance on a light bulb in a non-critical area? Of course not. You just wait for it to burn out, and then you screw in a new one. The key to a successful RTF strategy is making a calculated decision. It is only appropriate for equipment that is non-critical, where a failure has no safety implications and won't cause a domino effect of other failures or stop a vital process. It works best for components that are inexpensive and easy to replace, and for which you can keep spares on hand. You wouldn't use RTF for the engine on an airplane, but you might for the light in the galley. It's about understanding that maintenance resources are finite, and intentionally choosing not to spend them where the return on investment is effectively zero. It's the ultimate pragmatic choice in the maintenance toolbox. So there you have it, a tour through the essential strategies in the maintenance engineer's toolbox. From the disciplined schedule of preventive maintenance and the high-tech forecasting of predictive, to the all-in philosophy of total productive maintenance and the calculated gamble of run to failure. As you can see, there is no single best way. The right approach is a blend, a carefully crafted cocktail of strategies tailored to the specific needs of your equipment, your operation, and your goals. It's a dynamic process of balancing cost against risk and uptime against investment. The goal is to create a symphony of reliability where every part plays its role perfectly. Understanding these different types is the first step toward mastery. When you can look at a system and see not just its components, but also its potential failure modes and their consequences, you can start making truly intelligent decisions. You can move beyond simply reacting to problems and start architecting a future with fewer of them. This knowledge empowers you to build systems that are not only functional, but also resilient, efficient, and durable. It's how we transform a simple machine into a reliable partner, one that we can count on day in and day out. So I encourage you to take these ideas and apply them. Look at the things you build, operate, and depend on. Ask the questions. What is my strategy here? Am I being reactive when I should be proactive? Am I spending resources where they aren't needed? Choosing the right maintenance strategy is one of the most powerful levers you can pull to boost productivity, enhance safety, and slash downtime. Go build things, but more importantly, build them to last. Thanks for watching.